What's going on, everybody? It is Mr. Gustin. I'm in the physics conference room right now, and I've got an example problem for you. This is what I would call, it's resistors in series. We've got 3 resistors in series with the battery, and there's a capacitor attached parallel to one of these resistors. But essentially, when we turn this thing on, once it reaches a steady state, we have 3 resistors in series. So we're going to call this a series practice problem with capacitors, even though there's clearly a parallel branch to the capacitor. But the point is, I turn it on, the capacitor starts to charge. As the capacitor charges, once it's fully charged and reaches what we call a steady state, that means the capacitor is charged, then we have 3 resistors in series. And I got 2 questions for you, okay? First question, what is the initial current in the circuit? Now this requires some conceptual understanding of a capacitor before you can even do this. Where's my marker? And what we have to do is think about it this way. When I turn this thing on, when I first turn on the battery, consider each of these resistors to be light bulbs. When I turn them on, go back to think about the previous lab we just did, but go ahead and think about this. When I turn the battery on, charges will flow across this resistor, that light bulb is on. Charges will flow across this resistor, that light bulb is on. But I've got a resistor here, and then I've got a branch with no resistance in it whatsoever. It's a capacitor. Charges are free to flow. There's space on this plate for charges to store. They're going to move that way because there's no resistance to storing on the charge. Now, as this capacitor charges, now we start to get a backup of charge, or the charge can no longer fill these empty spots on this plate. Well, now charge starts to flow through here. This becomes dim and then brighter and brighter and brighter. And once this reaches its brightest point, we know this is charged. Once this light bulb is on, we call that a steady state. So let's conceptualize this. What is the initial current in the circuit? So initially, this light bulb is not on. And because this light bulb is not on, it doesn't include itself in the total resistance. Initially, the charge will flow across this resistor, stack up on this plate, push these charges back to the battery this way. So initially, if I wanted to look, I would say the total resistance is equal to, let's call this 1, we'll call that 2, we'll call that 3, is equal to R1 plus R2, because R3 is not even resisting charge yet. There's no charge flowing through R3 right away. Now again, as the capacitor charges, the charges go the other way. So our total is just R1 plus R2. So the total resistance here is going to be 16. The total or equivalent resistance here is 16 ohms. Now that's not my answer. My question is, what's the total current? So in this loop, I've got 16 ohms is my resistance. Let's use Ohm's law, VIR. The voltage is 12 volts. The resistance is 16 volts. I end up with a current initially of 0.75 amps. So that's easy. Straightforward, that's my initial current. The only conceptual understanding I have to have is that initially this resistor, this light bulb, resistor 3 is off. Now, at a steady state means the current has stopped changing, right? When you first plug in a capacitor in a circuit, the current starts to change. Either it goes up or goes down, usually goes down, but it depends on the circuit, right? The current begins to fluctuate. Once that current is steady, and it becomes steady once the capacitor is charged. So once it's charged and the current is steady, we call that a steady state. And that's the next kind of question I can ask you, right? So what is the potential difference across a capacitor at a steady state? So now I'm taking my multimeter. I want to know what is the voltage across this capacitor once it's reached a steady state. The first thing you have to answer, folks, is that current the current at the steady state, or is that the current at the initial condition? It's not the steady state, it's the initial condition. So the first thing I have to do, I gotta figure out what the current is at the steady state. Let's do that. At the steady state, my current, my charges, they leave the battery, or they are pushed from the battery. They move across this one. They move across that resistor. They reach this junction. Can charge flow through this branch once the capacitor is charged? No, it cannot. So there's no current going this way. It means the current has to go this way. So when I think about my total resistance at a steady state, that's R1 plus R2 plus R3. That's the total. When I add those up, I get R total to be 20 now. So that's a good, interesting finding. When a capacitor, I got resistors in series, a capacitor reaches the steady state, I see my resistance increase because now I've added a capacitor in series. I'm sorry, I've added a resistor in series. That should make sense to us. But that's my total resistance now at the steady state. The batteries remains unchanged. The battery, the chemical reaction powering this battery, whatever it is, still has 12 volts in it. So let's Ohm's law this thing again. VIR, I know that I've got 12 volts. I know that the resistance is now 20 ohms. I'm left with 0.6 amps of current at the steady state, okay? So anytime I am asked to find voltage or potential difference, I'm going to use loop rule. So let's find the loop. I want to find the potential across this capacitor. Here's my loop. All right, I got a battery, I got resistor 1, I've got resistor 2, I've got a capacitor. Though that's the loop back to the battery. I know that total voltage or change in voltage should be 0. Well, we've got the positive potential from, let's call it the battery. We're going to first subtract the current from resistor 1, or the potential lost at resistor 1. Then we'll go ahead and we'll look at the resistance, or resistor 2, the potential drop resistor 2, and then finally the remaining potential will be the potential difference at the capacitor. Battery supplies 12 volts, consumed, the total should be 0. Let's do some math. So I know I got positive 12 volts at the battery, minus the 0.6 amps at resistor 1. We said that was a 10 ohm resistor, minus the 0.6 amps at the second resistor times its 6 ohms of resistance. Bang, bang, bang. And I'm trying to find what VC is. Now, I plugged this all in my calculator. This is like 6 amps. This is like, I don't know, I think it's 3.6 amps here. So the remaining, I get the potential difference, or the drop at VC is equal to the 2.4 volts is the potential difference lost or across that capacitor. Anytime I see voltage or potential difference, you need to think loop rule. It's just right, it's right in front of you. It's right in front of you. It's so easy. You draw your loop, you write it out, you figure it out. So I've got 2 major takeaways. 1, initial conditions and steady state. They are different. Under initial conditions, the capacitor branch allows current to move through it. Not through it, but charges flow that way. At a steady state, charge will no longer flow around through, be pushed by this capacitor branch. It won't happen. Charges are not moving anymore when it's fully charged. That branch becomes essentially a dead branch. You treat it like it's not there anymore. Those are the differences between initial conditions and steady state. If you got questions, drop in the comments, send me an email, ask me in class. All right, till next time, see ya.